Hi folks, we're doing chapter 23, light geometric optics, so I'm going to review the slides and then I'll look at the problem set. Just a heads up, I'm not going to give you really complicated problems on this with a thin lens equation. I just don't see that it's that relevant, but some of these ideas are very important, especially the ideas about refraction. This is how optical fibers work. Okay, so let's take a look through the slides. It's a nice picture with a reflection on the water there, contents, and we start with a ray model of light. Okay, so hopefully again we're shooting these vertically, and so you can have something to the side of it. If you can't see the slides, you can look at the slides as well and follow along. So light very often travels in straight lines. We represent light using rays. So all this slide is saying, when it comes to geometrical optics, we consider light as a ray shooting around and we trace these rays. If you have watched the Mechanical Universe video, which I hope you have, I think it's a great video, because often when you do optics, it's really kind of dull because you have lenses and you have to solve the thin lens formula. But that's not looking at optics from a viewpoint of electromagnetism. The Mechanical Universe video, I particularly like that video because it looks at all of this, but from an electromagnetic point of view. How does the photons, the electromagnetic radiation, interact with matter to produce optics? So this chapter, we're looking more at it not from that point of view. So we'll do it quickly. It's sort of okay. But make sure you do watch that other video I mentioned. Okay, so we consider light as a ray, and we sort of trace the rays to see what the light is doing. Reflection, again, I think on the Mechanical Universe video they showed you the reason for this. You get a reflection because of the interaction between the electrical wave and the electrons in the material. As far as we're concerned, in this chapter we have light coming in. The angle of incidence is equal to the angle of reflection. So that's the law of reflection. We have two types of reflection. This is called diffuse reflection, and in this case we have light coming in. You can see there's this sort of a wave of light coming in this direction, but when it hits this surface is rough, so we get reflection in all directions. This is called diffuse reflection, and this is how we see things. This is to be contrasted with specular reflection, and here we go. Here's specular reflection. This is probably what you think of as reflection. When you look in a mirror, you have the light coming in, it bounces off, and you will only see that at one particular point. If your eye was up here, you wouldn't see it. But if we look at this surface, if you're looking at a pencil or something, the light comes in from a source, but it doesn't matter what angle you're viewing the pencil from, you'll see it, because we have diffuse reflection there, right? The light scatters in all directions, you see the thing, right? So there's two different types of reflection. Diffuse reflection, how we see things. Specular reflection, that's mirrors, right? That's what you think of as mirrors. If you do actually look in a reflecting surface, let's say this is just a mirror that you're looking into, and you had an object here, where would you see that object? Well, for that, what we do, we trace the rays. We imagine rays coming from this top point, hitting the mirror, and then combining over here, and we see, from our point of view, it looks as if the rays of light aren't coming from down here, but we can trace them back to over here. So it appears to us as if this bottle is actually behind the mirror. We call this a virtual image because the light rays don't actually ever go through it. It just appears to be a virtual image there. It appears like there's a bottle there. If you remember the display case outside the lab, there is a little frog, and the frog appears to float in air, and that's a virtual image. Maybe we'll take a video of it to add to the add to this. A virtual image, as I said, the light doesn't go through the reflection that you see in the mirror, and the distance of the image from the mirror is equal to the distance of the object from mirror, right? So d0 equals di in case of this reflection. Spherical mirrors are shaped like sections of a sphere. They can be reflective on either side, concave, or outside, convex. Think about caves. You go into caves, don't you, right? So the cave is the one that you go into, the one that goes back. Convex is the one that comes out, okay? So we don't have to have straight mirrors. We can actually curve the mirrors, okay? What we can do, we can actually get the rays and bring them to a focal point using a mirror, and this next slide shows that. So if we have an object, if this object is far, far away, then the rays, when they get close to this mirror, they're essentially parallel, and you can see that these two rays are brought to a focus here, right? So we would have this part of the tree focused at this point of the mirror. Isaac Newton invented the reflecting telescope, and when he did, he made a spherical mirror. I think he made it from a metal called speculum, as I recall, and it had advantages over sort of telescopes made from lenses. We haven't quite got there yet. Later in the chapter, maybe I should discuss that in more detail. But this is a mirror made from a circular section. There is a problem, you can see, that for these rays coming in, these parallel rays, they don't all come to the same focal point, okay? So a mirror, now it says here, if the curvature of the mirror is large, it means if it curves around a lot. I think this is a bit confusing because this has a small radius of curvature, meaning that it's very curved, right? So in this very curved mirror, the points don't come to the same focus. If we look at a mirror, again, this is a circular section, right? And the curve on this is much less, meaning that the radius of curvature is much larger, right? So this is a section of a circle, but it doesn't curve much. So if we go from a very curved circle here, very curved mirror, it doesn't bring it to the same focal point. But if we reduce the amount of curvature, then it does bring it to a focal point, okay? So we can make a telescope with a circular mirror, right? So we get part of a sphere and take that part of the sphere, and that would act as a telescope and bring the light to a focus. The ideal shape is actually a parabola, and I think Isaac Newton showed this. I'm not sure if he actually built a telescope with a parabolic mirror. I should check that. But if we do this, it works reasonably well. This C here, this is my radius of curvature R. So this is the center of the circle, and this is the part of the circle. What we find through geometry is that the focal point is midway between the mirror and the center, the center point of the circle. Okay, so we can say here, the focal point, F, we use F for the focal point, is the radius of the circle divided by 2. Let's go back. Here's the focal point F. This is the distance to the focal point here, and that's equal to the radius of the curvature divided by 2. There is a problem. Yeah, okay, this is what it says, spherical aberration, and this problem here is called spherical aberration. This can be avoided using a parabolic reflector, as I mentioned, but they're more difficult and expensive to make. You know, I guess expensive telescopes, if you, of course, use parabolic mirrors. Okay. Formation of images by spherical mirrors. We can use ray diagrams to figure out where the image is being formed. And what we do, we sort of imagine 3 different rays and emanating from the tip of the object we're observing, and we sort of trace them out and see where they join back up, and that's where the image would appear. It's probably easier just to look at the overhead, so I'm going to jump to this overhead one. Okay, we have the object here. Here's my object. We imagine a ray that leaves the object. It goes straight, it bounces off the mirror. Now we know that when it bounces off, it must go through the focal point. So that's the direction that ray goes. Okay? The second ray we consider leaves the object, goes through the focal point, bounces off, and comes out in the straight direction. If you think about this, this would have to work backwards, because if a ray of light came in along here, it would bounce back to the focal point. Okay? So that's the second ray that we've traced. The third ray we consider a ray of light which goes from the object, it hits the mirror such that this is 90 degrees, so it goes in and it comes straight back. And you can see that these three rays that we've traced out converge at this point here, and that means that that's where this part of the image is formed. What we could do the same exercise with any point on this arrow, and for example, if we did the bottom, we'd find that the bottom is there, right? So we've traced one point. If we want to see where the image is, we look at the bottom, we trace the bottom point, and we can see there is our image, okay? In this case, this would be a real image, right? Because the light is actually passing through it. So this forms a real image, and the image is actually magnified, right? There's the image, it's bigger than that image. This is a bit like a shaving mirror. Sometimes if you look in a shaving mirror, you look really big in it, okay? So the intersection of these three rays gives the position of the image at that point on the object. Get a full image, we can do the same with other points, and I think that's what I just said, okay? We can come up with this equation here. This is for mirrors. It looks very much like the thin lens equation, which you might have covered in physics already, but there is this relationship between the distance to the object, the distance to the image, and the focal length here. So again, these various quantities are defined here. This is the focal length here, 1/2 the radius, the distance to the object, the distance to the image. So if I know the distance to the object and the focal length, I can figure out the distance to the image, okay? The magnification will be HI over HO, and it can be shown it's equal to this quantity here. So ratio of the image distance to the object distance. The minus means that the image would appear flipped upside down, okay? If an object is inside the focal point, what happens then? Before we had the object coming out. Well, if we trace the rays, again, like we did before, we've got these three rays, we see that they don't actually converge on the outside, they converge over here, right? So in this case, what happens, we have a virtual image, which appears to come from behind the mirror, and it's enlarged. So we see a bigger image behind the mirror, okay? So that's what would happen in that case. If an object is outside the center of curvature of a concave mirror, its image will be inverted, smaller, and real. What's happening here? Here's my nose, here's the focal point, and I can only see that they've traced two rays, but I guess they cross over here. So this would be the image. You'd see yourself upside down if you're outside of the center of curvature. Remember, the center of curvature here will be twice the focal distance of, yeah, okay, they've marked it there. There's the center of curvature there, okay? So outside of the center of curvature, you'd see a upside down image. A convex mirror, the image is always virtual, upright, and smaller. Again, we have light coming in. Here's the rays coming in. Here's the rays coming out. If I was to view these rays coming out, it would appear that they all converge on this point here. So at this point, the focal length is negative, I believe. Here's an arrow. Again, we can trace the rays, and we see that this tip, it appears behind the mirror, so it's a virtual image, and the arrow is smaller. Okay. Don't worry about problem solving with spherical mirrors. We have some very simple problems on the worksheets, but I'm not going to give you any complicated questions on these. There's more interesting stuff to be had than this. Like this, the index of refraction. Now, I think this is kind of more interesting and relevant to our course. In general, light slows somewhat when traveling through a medium. That is a weird thing to say, because haven't we said that the speed of light is constant? How can light go slower if the speed of light is constant? Well, what happens is that the light is absorbed and re-emitted. Now, in class, what I often do is I get an object, a ball or something, and I throw it to someone, and then they throw it onto someone, and onto someone, and onto someone. And if we did that, what we'd find is that the time for the ball to get from the front of the class to the back of the class, for example, is longer than if I just got the ball and thrown it to the back of the class. In other words, the reason that it slows down, the ball slows down, is because people have to catch it and then throw it again. But the speed at which it's being thrown is probably the same. And so that's what happens with light. When light passes through a medium, it's absorbed and re-emitted. And so it appears to slow down. The speed of light is still the speed of light. It's just, it has to be absorbed, re-emitted. That takes time. Okay? So, if someone says that light travels slow in this medium, yeah, well, it does, but the speed of light is still the speed of light. The reason it's traveling slow is because of the absorption and re-emission. Okay? The index of refraction of a medium is a ratio of the speed of light in vacuum to the speed of light in the medium. Okay? So what we say N is C, this is that 3 times 10 to the 8 meters per second, over V, the speed of light in the medium. So here's the refractive index of some materials. Vacuum, of course, is 1. Air, that's pretty much like a vacuum, right? Slightly higher. Could this number ever be less than 1? No, because that means it's going faster than the speed of light, and nothing can go faster than the speed of light. So these values will always be greater than 1. Water, ethyl alcohol, and so on. I guess the interesting ones here are diamonds. Okay? Diamonds have a very high refractive index, and that's why they're sparkly. Right? So a diamond is kind of cool. It has an incredibly high refractive index. The wavelength, they've got the wavelength here. The actual refractive index depends upon the wavelength. So these are values at a specified wavelength. Okay? Different wavelengths, different refractive indices, and this is an important effect that we'll see. Okay? So this is Snell's law, and hopefully you've watched the videos. I did put some videos up on the Learning Hub, and I think there's one with a purple carpet and a truck or something like that. But all of them are similar. The way to think about this, and the way I like thinking about it, is that you can imagine sort of the Roman legions marching along, okay? And here they're on hard ground, and maybe this is sand. So imagine that Roman legion marching down. Now what happens is that the soldiers here, well, they get on the sand, so they start marching more slowly. So they start to bunch up, but these are still going fast. So this part slows down, well, that bit's still going fast because they're still on the firm ground. So what happens to the legion as it marches from the hard ground into the sand is that it bends around, right? And that's what happens because the light slows down, it bends around. On this diagram, we're being shown a reflected ray. We did talk about this a little bit. The reason is that we'll always get a reflection because the impedance changes. We looked at a video last semester, the vibrations and waves video, and we saw that when you have an impedance change, right, you get a reflection. So this would be a partial reflection at the boundary, but in this case, most of the light would pass through. If you look in a window, right, just stand and look into a window, you can see your reflection in the window. That's because of this effect, though most of the light's going through, okay? In this case, what's happening, let's imagine the Romans again, they're coming out of the sandy bit into the hard ground. So what happens is that the guys that come out first, these ones here, they sort of speed up, they can go faster now. These are still going slowly, so that side speeds up and it bends that way, right? Now, there is a relationship here, and it's called Snell's law, and Snell's law tells us the relationship between the indices, the refractive indices, and the angles, okay? When you're doing problems like this, we'll do a few. Try and draw a diagram of what's happening first, okay? So refraction is what makes objects half submerged in water look odd. If you look at this kid, his feet are in the wrong place and so on. What's happening is that the light from the feet is coming up like the Romans, and then this side hits the air, that speeds up, and so you can see that the legion would come like that side would speed up, and it bends in that direction. If we follow this ray back, it appears to the observer that the feet aren't here, but it appeared that the ray of light came from around where the knees are. So I'm sure you've seen this effect before. If you have a pencil in a glass of water, it looks kind of odd, and that's because of refraction, okay? So Snell's law, here's Snell's law, the angle of refraction depends on the indices of refraction, and it's given by this. So N1 sine theta 1 equals N2 sine theta 2. Let's just go back and look at it. So in this case, N1 would be air, theta 1 is the angle here, N2 is water, theta 2 is the angle here, okay? So that's Snell's law. Again, as I said, when you do apply this equation, try and write, do a little sketch and get in the angles. What's happening here, let's have a look. The light comes in from an object, from air. When it goes into glass, it slows down. Because it slows down, it bends that way. The first one's in go more slowly, and then when it comes out, it bends again, right? So it's kind of interesting that the angle is the same, right? So this 60 would be that 60. These lines are parallel. So you can see that it bends when it goes through the glass, but it bends back when it comes out of the glass. If you were to try and sort of, shoot someone through, don't try that. If you try to shoot someone through a piece of glass at an angle, you'd likely miss, right? Because you'd be shooting in that direction, seeing them here, whereas they'd really be there. I think that this is the same when you're trying, if you've got a spear fishing, when you're spear fishing, you don't aim for the fish, you have to aim at a different point because the fish isn't where you actually think it is, okay? Okay, total internal reflection and fiber optics. So again, this is an important idea. Let's just jump, I'm just going to jump to the slide. But imagine this is a dense medium where the light's moving slowly, and this is a rarer medium here. So normally what would happen, the light comes out and it bends around. So again, here's the Romans coming out. The first one's out, speed up, and it bends around. You can imagine that there is some angle where the bending is such that they're coming along. It's quite a shallow angle, you see, quite a shallow angle. They bend around, but they bend around such that they can't escape. And at any angle greater than the critical angle, it comes along, it hits the boundary, it bends around, and it's bounced right back into the material. So this is called total internal reflection, and this is how an optical fiber works. The optical fiber has the glass, in which the speed of light is slow, and it has a medium air on the outside where the speed is fast. And if I shoot light in this direction, it goes up and it bounces off, it reflects off the inside, not because it's a mirror, because of the indices of refraction. If you do get an optical fiber, of course, you can sort of steal information out of it, and you have a straight optical fiber, and all you have to do is bend it around, and when you bend it, you can imagine that you're changing the angle of incidence, and the light kind of leaks out of it, right? So there are ways to steal information from an optical fiber. This same process is used in binoculars. Here's a pair of binoculars. These are called poroprisms, and with a pair of binoculars, we want a long, we need a long focal length, and you don't want to have a pair of binoculars which is really long. So what you do, you have a long focal length, but you pack it up in a compact size. And the way you do this is that you have these two poroprisms, and the total internal reflection sends the light around on this convoluted path, increasing the focal length while maintaining a nice compact design. So if you remember the old days of, Jack Sparrow, what's that pirate movie called, Eleni?
Captain Hook.
Not Captain Hook. Oh, the Johnny
Pirates
Depp.
of the Caribbean.
Pirates of the Caribbean, right? Pirates always had long telescopes like that, right? But no one has a long telescope like that. You have a pair of binoculars because you've got that long optical path, and you've wrapped it up like that using these what's called poroprisms. This is the optical fiber. We have some of these in the display case outside, you might have noticed, but in this case it's a similar effect, but we send the light down here. So these have wide usage in electronics. One problem is, and I'm not sure, I'm going to talk about it now, we might get to it later in the notes, But one problem is, if we go back a few slides, this is at a specific wavelength, okay? What happens is that when you send information down a optical fiber, the different wavelengths travel at different speeds and the packet is sort of dispersed, right? So you have to sort of clean up the information, amplify it, and send it on again, okay? So optical fibers do have some limitations. The nice clean packets of information sort of get smeared out, they decay in strength, and so you have to sort of clean them up and resend them on the way at some point, okay? Lenses and ray tracing. So thin lenses are those whose thickness is small compared to their radius of curvature. They may be either converging or diverging. I guess these are converging lenses. I'm not quite sure what this is. Looks like he's looking down her throat or something. I really don't know. It looks like an eye. Anyway, they can be converging or diverging. This is a converging lens, and in a converging lens, the light rays are brought in and they're brought to a focal point. You can sort of think about this as sort of a series of prisms. You know, the light comes in, here's a boundary, and it bends like that, right? So we cause two bends. By changing these angles here, I can get it to bend twice and bring it to this point here. This is a thin lens, and it can be used to bring the light to a focal point. As I said, the actual index of refraction depends upon the wavelength. So how much light is bent around depends upon the wavelength. So one major disadvantage with lenses is that different wavelengths of light are brought to a different focal point, right? So blue light is refracted more than red light, and so the blue focus would be here, red focus would be there. So lenses aren't perfect. They suffer this effect called chromatic aberration, where different wavelengths are focused at different points. Diverging lens, here's a diverging lens, and in this case, rather than being brought to a focus at this point here, the light diverges out, and if I put from my point of view, it looks as if the image is actually behind the lens over here. Okay. The power of a lens is equal to 1 over its focal length in meters, and you might have come across this if you wear glasses. This is called diopters. I think I'm 1.25 diopters on mine, but the diopter has a unit of 1 over length. We can do the same thing we did for the mirrors for the thin lenses and trace rays, and again, let's just skip right to the diagram. Here's my object. Where does the image of my object appear when I look at it through the lens? Well, I consider ray 1, which hits the lens, has to go through the focal point. Ray 2, this has a focal point, a symmetrical focal point here, so that has to go through the lens and come out straight. Because I could get this point and I can trace it backwards. It has to work both ways, so this coming backwards would do that. The third ray goes right through the center of the lens and converges here. Okay? So there's my object, and this is where the image of the object will be formed over here. With a diverging lens, it's the same idea, only the image is upright and virtual. So if I look through this diverging lens, here's my object, and when I ray trace, I can see that the 3 traced rays converge at this point. So the object looks as if it's over here and it's smaller. Okay, so if you were here, we could get some lenses out and actually try this a bit. The thin lens equation, which you might have seen before, looks awfully like the mirror equation, but now we're defining things. I don't know if we have a diagram, but it's a distance to the image, distance to the object, 1 over the focal length. We have essentially the same equation for the thin lens as we had for the mirror. Okay. I'm not going to worry about this slide here. I think we have one really simple problem on the thin lenses in the worksheet. Again, I don't worry too much about these problems. The thin lens equation, again, the magnification is the ratio of the DI, distance to the image, and distance to the object. Again, let's not worry about that one. Look at combination of lenses. Here's the combination of lenses. If we have two lenses together, what happens? Well, we have to consider lens A. We have an object. Lens A forms an image here. And then that image is the image that's viewed by lens B. So we trace the rays from this point here, and we can see that there is the actual image formed there. So these two lenses in combination would actually form one single image over on this side here. The lens maker's equation, I'm not going to worry about that. Again, we don't have to cover this stuff in too much detail. That's the end of the slides. So, the most important point, I think, is to try and understand the index of refraction and understand how a fiber optic works. Other important ideas: a spherical mirror suffers from spherical aberration. A parabolic mirror can correct that. Lenses suffer from something called chromatic aberration. That's because glass is dispersive. When we say dispersive, what this means is that different wavelengths travel at different speeds through the material, right? So the different wavelengths of light travel at different speeds. You know what a prism is. How does a prism work? Well, the light comes in and it gets bent around. But different wavelengths are bent by different angles because glass is dispersive. So glass would spread white light out into a rainbow because it's dispersive. That looks good, that's nice, it's useful in some applications, but lenses, the lenses in my glasses, do the same thing. And that isn't good because then the different wavelengths of light are brought to different focal points. I know if you pay more for glasses, if we go back, the higher the refractive index, the less curved the glasses have to be. So ideally, if you wanted glasses which weren't very curvy, what would you make your glasses from? Any suggestions from the audience? Diamonds, right? So if you use diamonds that has such a high refractive index, it really bends the light. So you can use the lenses won't be very curved. But certainly I know that you can pay more, I guess the high index glasses, and if you pay more for your eyeglasses, you get the high index material, and they appear less curved but have the same power in diopters. Okay, let's finish there, and I'll try and look at the problem set now. Okay, I record it. Are you recording?
Yeah.
Okay, this is the mirror scope which I'd mentioned. I think maybe I described it incorrectly, but it's two parabolic mirrors. We have a frog down here, and when I put the sides together by some sort of magic, if you get the right angle, the frog, which is facing that way, from my point of view, I see a frog hovering up here, and I can put my finger right into the frog. I don't know how it looks on camera. Can you see it on camera? Where do you have to sit? But there we go. My finger, from my point of view, I can see a frog sitting above here. My finger goes in, I can put my finger right through the frog. That's what ghosts are. What? You see my head?